Section 3.1 Anatomy of 3D Printed Wall Systems. Moving on, let's talk about the anatomy of 3D printed wall systems. By now, you have already learned that OptiScore's main philosophy is to closely mimic or copy CMU block construction, but this is somewhat of an oversimplification. Here's why. When people think about CMU block construction, they typically think about a standard 8-inch thick CMU block, but there's actually a wide variety of different CMU block sizes and styles, and the same is true for 3D printed wall systems that mimic CMU blocks. Here are the three most common types of 3D printed wall systems. The 3D printed wall type you're most familiar with is the standard 8-inch thick wall. We often refer to this type of wall as an 8PB wall, which stands for 8-inch printed block wall. These 8PB walls are the most commonly recommended type of 3D printed wall for several reasons, including strength, familiarity, and versatility. As you learned in C3D 1100, these 8-inch printed block walls have a net area compressive strength of 2,640 psi with our standard print material, which is about 33% stronger than CMU blocks. This makes 8PB walls an excellent candidate for interior or exterior load-bearing walls, but they can also be used for interior partition walls as well. 8-inch CMU blocks are by and large the most common type of CMU block used in construction, which means there's a good chance your architect and engineer will already be familiar with this type of construction, or at the very least, they can find an abundant amount of information and wall details for 8-inch CMU walls. Also, most hardware stores and construction suppliers carry things like ladder wire mesh for 8-inch CMU block, and this is the exact same ladder wire mesh that's used to horizontally reinforce 8PB walls. For both 8PB walls and 12-inch printed block walls, the ladder wire is typically placed every 16 inches in print height. However, ladder wire for 12-inch walls is 4 inches wider than the standard ladder wire for 8-inch walls, and you should always use the proper size. Fun fact, we embed this ladder wire every 16 inches in print height because with CMU wall construction, ladder wire is most commonly placed every 2 courses of block. And since each course of block measures 8 inches tall, 2 courses of CMU block adds up to 16 inches. However, if you happen to be in one of those few areas where local building codes require ladder wire to be placed between every single course of CMU block, then your engineer will likely require you to place ladder wire every 8 inches in print height instead of every 16 inches like most places permit. One last thing about these 8PB walls is versatility. These walls are versatile because they contain 3 inches of cavity space, which can accommodate up to 2.5-inch plumbing pipes and electrical conduit, while maintaining a relatively low profile when compared to the 12-inch printed block walls. This means that you can realistically use 8PB walls throughout an entire building without sacrificing strength or living space, and without needing to surface mount plumbing and electrical. So, if 8-inch printed block walls are so great, why would anyone want to print 12PB walls or 12-inch printed block walls? Well, there are a couple of reasons why you may decide to use 12PB walls over 8PB walls, particularly when it comes to exterior load-bearing walls. First, these 12PB walls are only 4 inches wider, but that's 4 extra inches of pure open cavity space inside of the wall, which can be filled with insulation to meet our value requirements in colder climates. Stepping up to the larger 12PB wall means going from 3.5 inches to 7.5 inches of wall cavity space, which more than doubles the total amount of insulation that you can incorporate into these 12PB walls. We'll cover insulation in depth later on in the course, but for now, let's stay focused on the anatomy of these 3D printed block walls. Another advantage of these larger 12 pb walls is that they typically require less vertical reinforcement than 8 pb walls. This is because 12 pb walls have a broader 12-inch profile, which can provide better lateral support than the more narrow 8-inch printed block walls. This makes sense when you think about it. For example, if you stand upright with your feet together in a narrow stance, it doesn't take much force to make you lose your balance. But if you separate your feet and take a broader stance to give yourself more lateral support, then you're much more stable and it'll take a lot more force to push you over. When it comes to wall systems, the broader the profile also equates to a greater amount of surface area that is making contact with the slab and binding the layers together. This is why 12 pb or 12-inch CMU walls often require less vertical reinforcement than 8 pb or 8-inch CMU walls to meet the same structural requirements. In practice, 8-inch walls often require vertical reinforcement every 2 to 4 linear feet, while 12-inch walls often require vertical reinforcement every 6 to 8 linear feet. For 8 pb walls with reinforcement every 2 feet off center, there would be 2 cavities of insulation between each reinforced cell. But for 12 pb walls with reinforcement every 6 feet off center, you could have 7 insulated cavities between each reinforced cell. In theory, this means a straight 8-inch wall measuring 100 linear feet could require 50 reinforced cavities, while the same 12-inch wall could only require about 17 or 18 reinforced cavities. That's significantly less rebar, grout, and epoxy, and much more insulation instead. However, I should mention that not many houses are built with long straight walls like this, and in practice, you will need to add reinforcement on both sides of every window and door opening, at every end cap, and at every sharp corner, regardless of the type of 3D printed wall system you're using. If you didn't catch all that, don't worry. We'll have a whole chapter dedicated to methods for reinforcing 3D printed wall systems. Now, before we move on to discuss the 6-inch printed block walls, I want to mention one last thing about the infill pattern for both the 8 pb and 12 pb walls. You'll notice that the near side of both of these pictures depict the end cap of a wall section. This could be an opening for a window or door, or just the end of a straight wall section. You can see that the infill doesn't stop when it reaches the first corner of the end cap, but rather, the infill continues across to create a double thick layer behind the face of the end cap. This double layer end cap provides 3 primary functions. First, it helps to reinforce the end cap and reduce the risk of accidental damage. Second, the extra material provides additional traction for masonry screws when securing windows and doors. And third, the added material helps to support the weight of the window and door lintels when they're being installed on freshly printed layers. Now, let's turn our attention to the 6-inch printed wall. The most obvious difference is that these 6-inch walls do not contain any infill material, and thus we do not refer to this type of wall system as a printed block wall or PB wall. Instead, refer to these as hollow printed walls or HP walls. On their own, these HP walls are not considered structural or load-bearing walls, although it is possible to incorporate reinforcement into these hollow printed walls and then fill them with structural concrete to create a load-bearing mass wall. In this case, the 3D printed wall is used as a type of permanent formwork instead of a standalone 3D printed structural element. When you look at most 3D printed buildings, excluding those printed by OptiScore, this kind of hollow print pattern without any infill material seems to be one of the most common. However, I would not recommend this method for exterior walls for a few reasons. First, it's likely going to be more difficult to obtain a building permit for hollow printed exterior walls because they do not mimic CMU block walls like the PB walls do. Second, because you're probably going to have to sacrifice insulation value to properly reinforce these walls, or vice versa. A common compromise is to use structural lightweight concrete because of its combination of structural and insulating properties. But at only around R1.85 per inch, it would require about 7 inches of lightweight concrete inside of a 10-inch hollow print wall to achieve an insulation value of R13, and you may be required to have up to an R21 insulation value or greater in colder regions. As seen here, another compromise is to print wall cavities for reinforcement without using a separate dedicated infill layer. The problem with this method is that you end up with these unsightly wall indentations, which personally I don't find particularly attractive. It would be easy to patch a few of these up between print sections, but if every reinforced wall cavity creates 2 of these indentations, then you'll probably have to patch multiple joints in every single room in the house, and that can get expensive. This is why it typically makes more sense to simply use the printed block walls instead of hollow printed walls on the exterior of a building. However, these hollow printed walls can be used on interior spaces where they don't need to be insulated or provide structural support. It's also easier to top out plumbing inside of a hollow printed wall cavity, especially when it comes to horizontal piping, which may be used, for example, to tie the vent pipe from a sink into an adjacent main vent stack. We'll cover plumbing in depth in a later section. On the topic of these HP walls, you may be surprised to learn that virtually every printed block wall will contain some hollow printed layers. And this is no accident. It's done to mimic CMU construction. The type of CMU blocks that are used to build the very top course in a properly constructed CMU wall are actually a unique kind of CMU block that's different from all the other standard CMU blocks below. These blocks are called bond beam blocks, and they contain less webbing or infill than the standard CMU block. As you probably guessed, these bond beam blocks are used to create the bond beam at the top of the CMU wall, but are also commonly used to connect floors on multi-story buildings and at the top of foundation walls or stem walls. In all of these scenarios, the bond beam blocks will need to be horizontally reinforced with rebar and grout, and this is why a portion of the webbing or infill has been removed to accommodate the reinforcement. Bond beams are structurally very important because they help resist shear forces and provide horizontal strength to prevent entire wall sections from toppling over. They also serve as the connection point between critical structural elements, like connecting your roof system to your wall system so your roof doesn't fly off during a hurricane. That's why printed block walls also contain some hollow printed bond beam layers. Now, let's take a step back and compare these 3 types of wall systems. The first thing we'll look at is the material weight per square foot. The 6-inch hollow printed walls contain approximately 31.4 pounds of print material per square foot of wall area. The 8-inch printed block walls weigh about 51.2 pounds per square foot, and the 12 PB walls contain approximately 59.1 pounds per square foot. One thing you'll notice is that there's only about a 15% increase in material weight per square foot when you move up from the 8 PB wall to the 12 PB wall. And that's because we're only adding a relatively small piece of infill. And remember, that small 15% increase gets you an extra 4 inches of open cavity space, which leaves more room for insulation, plumbing, and electrical. However, when you compare 6-inch hollow print to the 8-inch printed block, we see a roughly 20-pound difference in material weight per square foot, which equates to roughly 62% savings in print material for the 6-inch hollow print versus the 8-inch printed block. This is why these hollow printed walls are not structural or load-bearing, but they can reduce material consumption on interior non-load-bearing walls, and their lighter weight can make them a better option to use on the second-story walls to reduce the dead load on your floor system. Now that we have an understanding of the conventional types of 3D printed wall patterns, let's zoom out and explore how these layers stack up to form a 3D printed wall. This is a simple 3D printed wall section, which includes one window located in the center of the wall section, and a precast lintel above. At 20 millimeters per layer, Frank will need to print 152 layers high to achieve this wall's 10-foot overall print height. But not all of these layers will be printed using the exact same toolpath. In case you aren't familiar with the term toolpath, a toolpath is the path the extruder will follow as it 3D prints each layer. You can see here that the layers at the base of the wall section will be continuous and span the entire 10-foot length of the wall section, but as we continue printing higher, we'll eventually have to create this window opening here. This will require a different and unique toolpath, which is not continuous, and will exclude the central area where the window will be installed. Just above the window opening, we have our precast lintel, which means we'll need to leave an additional opening that is even wider than the window opening to accommodate this lintel. And as you probably guessed, this also means that we will need another toolpath. Let's take a second to have you think about how many different toolpaths are needed to print this one wall section. Do you think it will take 3 different toolpaths, 4, or 5 different and unique toolpaths? If you guessed 4 different unique toolpaths, then you are correct. But this is also kind of a trick question. Let's break this wall apart into its different toolpath sections to explain why. Here you can see 5 different sections and a lintel. Starting from the bottom, we can see the continuous base layers, which span the entire length of the wall section. We'll call this toolpath number 1. Moving up, we can see toolpath number 2 to accommodate the window opening. Then, toolpath 3 to accommodate the precast lintel. Now, here's where it gets a little tricky. The next section above the lintel opening is another continuous toolpath that spans the entire width of the wall section, but this is not a new and distinctly different or unique toolpath. In fact, it's the exact same toolpath that we used on the base section, so we'll call it what it is, toolpath number 1, again. Finally, we reach the top of the wall section where the bond beam is located. These layers do span the entire width of the wall section, but they are hollow print layers, which do not contain any infill pattern. This section of bond beam layers will have a distinctly different toolpath. We'll call this toolpath number 4. Now, you may be wondering why this toolpath matters, and the short answer is that the toolpath is essentially what determines or defines the anatomy of a 3D printed wall. From this visual perspective, the toolpath sections are clearly visible, but the toolpath itself is hiding some important information. Let's take a closer look and examine what's going on inside of the wall section. Starting with toolpath number 1, which makes up the base of the wall section, we can see 2 distinct areas, here and here, where the infill pattern has some unique features. If this wall section did not contain a window opening, then the toolpath for this infill pattern would remain continuous and uniform across the entire wall section. However, the addition of the window opening, or toolpath number 2, has a direct effect on toolpath number 1 and toolpath number 3. In fact, the addition of any wall portal, such as a window or doorway, will have a direct effect on every toolpath across the z-axis, with one exception, that is, the toolpath for the bond beam layers may not be affected. The bond beam layers will likely remain unaffected because the addition of a wall portal will only affect the toolpath of the infill material in the neighboring section. And since the bond beam layers do not contain any infill material, in most cases they will remain unchanged. Looking back to those unique features in toolpath number 1, we can see that the infill pattern has been modified to create a double layer of infill material that is directly below both of the window opening's end caps. You should remember that the double layer end cap provides 1. Additional reinforcement, 2. A stronger connection point for window and door frames, and 3. Support for the lintels. However, if this double layer end cap is used in toolpath number 2 for the window opening, then the infill pattern in toolpath number 1 must also contain a double layer in order to support the material above. Without this, the unsupported layer would simply fall to the floor and most likely drag some additional material down with it. Now that we know why our toolpath number 1 base layer contains these 2 double layers, you may have also noticed that the 2 cavities on either end of the double layer are slightly smaller than the other wall cavities. The answer to why this is can be found in toolpath number 3 for the precast lintel. Precast lintels contain knockouts at either end of the member, which are basically 2 notches that are carved out of the bottom of the lintel to accommodate rebar reinforcement and grout. This rebar and grout reinforcement will form a structural column within the wall cavities at either end of the wall portal, but there are requirements for how large these reinforced columns should be. Looking at our sample wall, we can see the size and volume of this wall cavity will increase as this piece of infill moves away from the window opening, and it will decrease in size and volume as this piece of infill moves closer to the window. The important fact to remember is that as this piece of infill on toolpath number 3 is shifted to create the required column size, the other infill toolpaths below will also need to be adjusted accordingly. When we view this 3D printed wall section from above, we can look down into the wall cavities and see that all of the toolpaths perfectly align to create uniform cavities that maintain a consistent size and shape from bottom to top. This may sound like a lot of adjustment and modification for the G-code developer, but as you'll see in a later section, APISCore's AutoCAD plugin makes it easy to incorporate windows and doors into your G-code. Now, I know that many of us learn better with the help of something like this, a physical model that we can touch and feel in addition to the digital illustrations and renderings that you have seen here in this video. That's why we included a free STL file of this exact scale model so that you can 3D print and assemble your very own scale model of a 3D printed wall. You can find the link to download this free file below this video. Now, let's take the information that we've learned in this section and compile it into a 3D wall detail. We'll piece together a masonry wall and an identical 3D printed wall side by side so you can see how the two compare. Both wall systems start with a slab, which you can see pictured here at the bottom. Vertical rebar dowels are then anchored into the slab and project up through the slab surface. Later on, continuous wall reinforcement will be securely tied or coupled with these vertical dowels. Next, it's time to begin erecting the wall. Ladder wire is embedded into the CMU wall between the second and third courses of CMU block, which is 16 inches above the slab surface. The same is done for the 3D printed wall. 2 more courses of CMU block are laid, and ladder wire is once again embedded between the 4th and 5th courses of block. The same is done for the 3D printed wall. The next 5 courses of CMU block will include a window opening in the center of the wall, and ladder wire, which will continue to be placed every 16 inches. Again, the same is done for the 3D printed wall. Now that the window opening has been finished, the next course of block will include a precast lintel to support the window opening. And of course, the same is done for the 3D printed wall. A piece of horizontal rebar reinforcement is then placed inside of the precast U-lintel for additional reinforcement in both the CMU wall and the 3D printed wall. Now, here's where things can get a little tricky. There are still 2 more courses of CMU block that need to be laid before the bond beam begins, which means that there's 16 inches of additional printed block with infill material that need to be printed before we can start printing the bond beam layers. The problem is that the U-lintel is hollow in the middle, so it needs to be grouted and leveled so we have a flat surface to support that infill material before we can continue printing the rest of the wall. There are a couple of solutions here. The first solution is to avoid this problem in the first place by designing window and doorway openings so the bond beam starts immediately on top of the lintel. With taller walls, this typically means placing windows higher up on the wall, or using taller windows and doors. However, if you really don't want to make these minor design modifications, you can always grout the lintel without grouting the adjacent wall cavities. This way, you have a flat surface to print on without having to grout entire wall cavities mid-print. A lintel this size would only require 1 to 2 bags of fast-setting concrete, and some plastic grout-stop mesh should help it from falling into the adjacent wall cavities. This is fairly easy to do, and it doesn't take very long. Once that's done, you can print the remaining 16 inches and lay the remaining 2 courses of block before reaching the bond beam. The CMU wall will require special bond beam blocks to be used for this top course to accommodate the bond beam reinforcement, and the printer will print these final bond beam layers without infill material to do the same. Now, we have 2 walls that may look finished on the outside, but they still do not have insulation or reinforcement on the inside. Insulation is added inside of the wall cavities first. This way, the vertical wall cavities and horizontal bond beam can all be grouted at the same time. With CMU construction, it's commonly required to cut a cleanout hole in the bottom of each reinforced cell, so any extra mortar that fell into the cavity can be removed, and so the building inspector can verify that the rebar is properly tied. Unlike a block mason, Frank the 3D printer doesn't drop extra material into the cavities, so there should not be any mortar to clean out. For this reason, it's possible that you won't need to cut cleanout holes at all, but if you do, a 4-inch hole saw should do the trick. We'll talk more about reinforcement and why using rebar couplers or hammer-in adhesive anchors could help you avoid needing cleanout holes in a later section. In any case, vertical rebar reinforcement is dropped into the wall cavities, and then the final step is to pour grout into the walls to cast all of the reinforcement in place. Later on in the course, we'll refer back to this model and take you with us out into the field to show you how to attach roof systems, install windows and doors, and add various types of finishes to these 3D printed walls. Now that you know the basic anatomy of a 3D printed wall, you're ready to jump into the next section, where you'll learn how to apply this knowledge and create 3D-friendly architectural designs.